Hello, calculus students. It's good to be back with you this week. We're going to do a real quick lesson on Lagrange error bounds, so when we come into class tomorrow, we can get rocking and rolling right away. First of all, anytime you're using a Taylor polynomial or Maclaurin series to approximate an actual value of a function, for instance, we could approximate sine of like 0.7 with a Maclaurin series, and we could go up to, let's just do the third degree. So it would be x, or 0.7, minus x cubed, 0.7 cubed over 3 factorial. And then the next one would be x to the fifth, which would be 0.7 to the fifth over 5 factorial. But if we were going to approximate it just with a third degree series, we'd have something like that. We could figure out what that is either by hand or in our calculator, and that would be an approximation. But it's an approximation. It's off a little bit, just like when we had our graph. We showed the graph of the Maclaurin series and how it would hug the function, but it would be a little off as we got to a certain point. So this guy's off a little bit, but the Lagrange error bound tells us how much it is off by. So this fancy formula is saying if you have the actual function and we subtract off the polynomial, so here's your actual function, we subtract off the polynomial approximation. So on your calculator, if you did sine of 0.7, you'd get some value. And then if we figured out what this was, the sine of 0.7 with our Taylor, our Maclaurin series, we get this polynomial approximation. And we subtract those two, and what you're left with is the remainder, or the error. This is the error of our polynomial approximation. Okay, so I've totally made a mess of this page. Well, basically, Lagrange came up with this way to find the error of a polynomial approximation if it wasn't alternating. We know the alternating series, if we want to get the error of a convergent alternating series, we can just go to the next term. We talked about that already, but sometimes series are not alternating. So Lagrange came up with this way to deal with those non-alternating series, what the error would be. This fancy formula is really not as bad as it seems. Remember, if we were to do like a third degree polynomial, it would be x to the third over 3 factorial times the third derivative at its center. Well, basically what this is saying is if you want to find the error, this r, remember, is remainder or an error. If you want to find the error of a, let's say, 5th degree polynomial approximation, so we'd put 5 in for n, we'd go to the 6th derivative, and then we have to plug in this value. That's where, this is what gets a little tricky on this. We're going to plug in this value of c, and then we'll multiply it times, you know, x minus ar. This is what we put in all of our Taylor expansions, to the 6th power over 6 factorial. Remember, it was 6 derivative, 6 degree, 6 factorial. Well, this c value that we're plugging in up here, we have to find the largest derivative between the value that we're plugging in for x, what we're trying to approximate, and the center. So we have to figure out which derivative, which number will give us between a and x. So a is the center. Maclaurin series, remember, is centered at 0. X is what we're actually trying to approximate. So in this case, it would be 0.7 we'd put in for x. We're trying to figure out the derivative somewhere between these, the largest derivative, the largest n plus 1 derivative, somewhere between a and x. So basically what we're going to do is we're going to plug in a and we're going to plug in x, and we're going to see which one is bigger when we get to our derivative. Okay, I think this will make more sense once we do a couple practice problems. Okay, so let's say we're looking at e to the x, and we are going to go to a third degree Maclaurin series, and we're going to approximate it at x equals 0.2. So our center is 0 because it's a Maclaurin series, and then we're going to use this x equals 0.2. So we have to choose between a derivative at 0 or at 0.2. Now, we don't just want to use the first derivative. We're using a third degree Maclaurin series to approximate it, so we have to go to the 4th derivative, f4, of some value. We're going to either use 0 or 0.2, and then we're going to multiply that times x to the 4th. Remember, the 4 4, and then over 4 factorial. That's going to be how we figure out what our error is. This guy is going to give us our error. Well, actually, our error is going to be less than that value. So, looking at e to the x, if we want to do the fourth derivative of e to the x, let's look at that first. Let me erase this real quick. Our fourth derivative of e to the x we know is e to the x. So now we need to think, if we plug in 0, e to the 0 is 1. If we plug in 0.2, well, you got to think about this visually. Here's 0, here's 0.2. This guy's going to be a little bit higher. So we are going to plug in 0.2 for our fourth derivative. So we're going to do f for a 0.2 equals e to the 0.2. Okay? So our error that we just found is going to be less than the absolute value of e to the 0.2. We're going to plug in 0.2 for x because that's what we're trying to approximate. 0.2 to the fourth over 4 factorial. And I'll let you calculate that on your calculator, or you can do it by hand. While the e to the 0.2 might be a little tricky, that's the error of your series. Okay? That's called a Lagrange error bound. So let's try another one. Maclaurin series again, we're using a 5th degree. We're looking at sine 2x. This is alternating. Remember, sine x is going to be 1 minus x squared, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And we could keep going. This is alternating, so instead of using Lagrange error bound, which I think is a little confusing, we're just going to use our alternating series rule, where we're just going to do sine 2x, and we're going to go to the next term. So we'd have 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial. Okay, so if we plug in 0.5 in for x, using a 5th degree polynomial, this is what we get. Okay? But we want to figure out what the error is. So the error is going to be less than the next term. Will be less than the absolute value of 2x to the 7th over 7 factorial. We don't want to use a vanishing term. We're not going to use a 6th degree term. We're going to use a 7th degree term. And that will be 2 times 0.5, so we're going to put 0.5 in here for x. Well, that's pretty easy. 2 times a half is 1 to the 7th over 7 factorial. So our error is less than 1 over 7 factorial. Okay? Okay. Here we go, one more. We have e to the x. Again, we're going to use 3 terms of a Maclaurin series, which means my center is at 0. And we know that x is, we're going to use some value of x that's less than 0.1. So let's just use x equals 0.1 to get our error. So 3 terms this time instead of the 3rd degree. So if you think about e to the x, that's 1 plus x squared over 2 factorial. Okay, that is 3 terms already. So we're going to use the 3rd degree. So we need the 3rd derivative of x times x to the 3rd over 3 factorial. All right, whoops. We're going to figure out what that value is there. Okay, so our error, again, we know any derivative of e to the x is just going to be e to the x. If I plug in 0 versus 0.1, this is going to give me the largest value, e to the 0.1. So my error is going to be less than e to the 0.1. Remember, the derivative of e to the x, no matter how many times you take it out, is e to the x. So that's why I'm doing e to the 0.1, because I'm putting 1 in for x, times 0.1 to the 3rd over 3 factorial. Your error will be less than that value. It's not too bad. Okay, this next one, we are going to approximate sine x with a 3rd degree Maclaurin series. This is a little bit different because they want the error to be no larger than this number. So my error is no bigger than that guy. All right, sine is alternating. Third degree, that means we're going to go to the fifth degree term because the fourth degree in sine is vanishing. So I know my error has to be less than the fifth degree term. So let's see, we're going to do, what do we say, fifth degree, so we're looking at x to the fifth over 5 factorial. We're trying to figure out the x values that won't have, we're trying to figure out the x values where the error will be no greater than that. Okay, so let's go ahead and plug in our error. 5 times 10 to the negative 4 has to be less than x to the fifth over 5 factorial. So then x to the fifth, if we multiply across, is going to be greater than 5 factorial times 5 times 10 to the negative 4. Okay? Error has to be no more than that. So there is your first 4 examples. And that's all I got for you. Okay, sorry about this. We're going to back this up a little bit. I was just about to get off this page and I realized I put the absolute value around the wrong thing. So our absolute value is really going around that. So that means our error, well, let's fill in the error. We were told that this is our error. So that means 5 times 10 to the negative 4 is less than the absolute value of x to the fifth over 5 factorial. Something seemed wrong. So what this is telling us, if we split this up, we have x to the fifth over 5 factorial is going to be less than, I'm sorry, it's going to be greater than 5 times 10 to the negative 4. Well, no, let's do it this way. Okay, I'm getting myself all messed up here. Okay. Let's just shift this around. We know that the absolute value of x to the fifth is going to be greater than 5 factorial times 5 times 10 to the negative 4. All right, and then we need to, I'm really messing this up. We're going to start over again. Okay, you guys, major brain freeze. Sorry. We're going to start this over again. We've got an error that is less than 5 times 10 to the negative 4. We know this is alternating. We're using a third degree to approximate, so we're going to go to the fifth degree term because the fourth degree is vanishing. So I know the absolute value of x to the fifth over 5 factorial is less than 5 times 10 to the negative 4. Okay? So sorry about this. So let's do a little algebra. That means x to the fifth in absolute value is less than 5 times 10 to the negative 4 times 5 factorial. Okay? Using more algebra, we have x to the fifth is less than, by the way, that number is 0.06. So x to the fifth is less than 0.06. This guy right here is 0.06. Or greater than negative 0.06. Remember that from algebra? Yeah, I was having a brain fart. I forgot. Okay, so now we're going to take the fifth root of both sides, and we get x has to be less than 0.569 and greater than negative 0.569. What this is telling you is that you can plug any values between negative 0.569 and 0.569 in for your Maclaurin series for sine x. You can plug any number between those and you go to the third degree and you will get an error that is not going to be any bigger than this number. Okay, I hope that straightened it out. So now what I want you to do is try the homework which is on the back of this worksheet. And I will go through those also on a different video, so check those out. Okay, I'll put the answers up in case you just want to check the answers. I'll also do a video of it. Okay, thanks. Bye-bye.